In this video, we're going to continue section 3.3, and I want to find intervals where a function is increasing and where it's decreasing using the derivative. So if we're going to use the derivative, the function had better be differential. So consider f of x equals, let's say, x cubed minus 3x. Find intervals where f is increasing and intervals where it's decreasing. Okay, so we're going to use that theorem that we proved in the last video. We're going to take the derivative and figure out where it's positive and where it's negative. We know how to do that because at the beginning of the course we did an intensive review of pre-calculus and we learned how to do sign charts. So let's go ahead and take the derivative. F prime of x equals derivative of x cubed is 3x squared. The derivative of 3x is 3. And we can factor this. We can factor a 3 out. And we can certainly factor x squared minus 1. So let's do a sign chart. We can see that the derivative, oh, sorry, this is not a sign chart for f, this is a sign chart for f prime. We can see the derivative is equal to 0 at x equals 1, and at x equals minus 1. That takes the real line and breaks it up into 3 parts. 1, 2, 3. And in each of those parts, we are going to take a value of x and plug it in to the first derivative. We're interested in doing a sign chart for the first derivative, so we have to plug everything into the first derivative. So f prime, let me pick a point to the left of negative 1. How about negative 2? F prime of negative 2 is equal to 3 times negative 2 squared minus 3. That's 3 times 4 is 12, minus 3 is 9, which is certainly greater than 0. Let me pick a point between negative 1 and 1. How about 0? 3 times 0 squared minus 3, which is negative 3, which is less than 0. It's negative in there. Oops, f prime. And f prime of 2, a point to the right of 1, equals 3 times 2 squared minus 3, which is 9 again, which is certainly positive. According to the theorem that we proved, where the derivative is positive, the function is increasing to the right. So where we see plus signs, I'm going to put little arrows going uphill to the right. I'm always going to put my arrowhead on the right-hand side. And wherever I see minus signs, I'm going to put arrows going down to the right. And so I can see that my function is increasing on negative infinity all the way up to negative 1. You could use an open or a closed set of a closed bracket or open parentheses. I'm going to put open parentheses here right now. And it's also increasing from 1 to infinity. It's decreasing where I see the minus signs, where I see that down arrow. That's from negative 1 to 1. I didn't ask, let me get rid of the arithmetic over here. If I said state and classify all critical points, call this part A and this part B. If I said state and classify all critical points, remember the definition of a critical point. It's a place where the derivative either equals 0 or doesn't exist at all. Now, this is clearly a differentiable function. It's a polynomial. It's nice and smooth, and you can see that it has derivative everywhere. But at two places, the derivative is equal to 0. At x equals -1 and at x equals 1. At x equals -1, I'm asking you, is that the top of a hill? Is it the bottom of a valley? Top of a hill, local maximum. Bottom of a valley, local minimum. Or is it none of the above, like in the x cubed curve? Well, we can see the function going up and then going down. At x equals -1, we must be at the top of a hill. You can see it from the arrows, up, down. So x equals -1 is a relative or a local maximum. At x equals 1, you can see it, again, there's a flat point right there. It's actually, if it's going down and then going up, it must be at the bottom of a valley. It must be a local minimum, a relative minimum. And so we can use the first derivative not only to tell us where the function is going uphill to the right and where it's going downhill to the right, but also to find and to classify the critical points as maxima, minima, or neither.